bosons. We've started with that already.
Tanguy? Is that? Sorry, please go ahead.
Invitation. I don't know if the organizer knew the content of the previous talk before mine talk. I thought it would be a bit different, but actually it's exactly on the same topic. But I will be a bit less optimistic. Sorry for that. But I think it will be interesting. I just collected actually the different data from Auger in particular, and to see what are the constraints if you really want to explain that with new physics. So which at the end is actually not that easy. I would say that there is not so much room, and we will see with the study from Oliver and others what they can extract from that. That would be quite interesting when they take everything into account. Starting, Oliver already showed something very similar to this plot. And yeah, the goal is really to remind you the energy we are talking about. And what is very important to remember is that LHC is at about 10 to 17 electron volts, as it was said. So in terms of electron volts, 17. And we extend really to up to 10 to 20 electron volts. But muon measurements actually are up to 10 to 19.5 or something like that. Okay, so just to remind you that the problem, or what we want to do with astroparticle physics and the cosmic rays, is to study astrophysical objects. So it's some kind of astronomy in principle. But for that, what you really need is to try to extract the energy. This we know more or less how to do up to, with a kind of 15% uncertainty. A direction that we know very well, but since this is charged particles, it's actually complicated to trace back the source. In particular, if you have heavy composition. So what is very important and what is really the problem now is to get the composition of primary cosmic ray and to really interpret correctly their interaction with the electromagnetic, the magnetic field in the universe or in the galaxy. And on the right here, you see the current status of the mean LNA. So this is the logarithm of the mean logarithmic mass of the primary cosmic ray. You have this yellow band here, which is already quite large, and it's coming from this Xmax that Oliver explained. So from the electromagnetic component, basically, which in principle helps to constrain the different lines, which are different astrophysical model. But the problem with Xmax is you get only 10% of the time when you measure that you need moonless nights. So there is another measurement that you can do all the time. It is the number of muons. And from the number of muons, you can also extract the mass. But this big band behind is actually what you get now, which is covering a very large range from which you can basically do nothing. And this is really due to the uncertainty we have in the hadronic interaction and the air shower simulation. Because, yeah, by definition, you have a degeneracy between the mass of the primary cosmic ray and the basic properties that lead the shower development. If you change the mass, you change the cross-section, you change the multiplicity, you change elasticity. So you change everything which really will define Xmax at the end. So you need to know hadronic interaction if you want to have proper composition, or if you don't have and if you don't have data at some energy like above LHC and even above FCC, which we never go beyond. So you need some trick to do that. So you can measure actually the mass from different methods, like here, from the number of muons from Xmax, and then you can compare. And if they don't match, it means you have a problem, and you can try to improve your hadronic interaction. So that's what we are trying to do. So, and to explain this large number of muons, is there room for new physics? That's the idea. So what do we use as a standard model in our case? So to extract signal from air showers, it's actually quite a complex problem. Basic ideas are very simple, but in practice, it's billions of particles and yeah, millions of interactions. So it's a numerically complex problem. And for that, we have hadronic models, hadronic interaction models, which are based on QCD. But the problem is that this is a non-perturbative regime of QCD, which dominates this minimum bias interaction. So it's really the main source of uncertainty in air shower simulation. And the model we use are not the one you are familiar with. We have heavy ion community here, so maybe a bit more familiar, but so you have DPM Jet 3, which can be used, but is not yet very much used, especially the latest version. EPOS, of course, so I'm one of the authors, and this you know, I guess, for heavy ion simulation. You have QGIS-JET with different versions. We started in 2000 with QGIS-01. Now we have QGIS-2.4, and maybe later QGIS-3 from Sergei Ostapchenko, which is a theory-based model where you have a lot of very nice ingredients, but then in limited number of observables. And you have Civil, which is also a kind of simple approach, PTI-like pattern-based model, but much simpler, with less details, but very fast and really optimized for cosmic rays. And you will see reference to these models. And just to give you an idea, so they are all based more or less on the same idea, of course, which is the standard model, starting with perturbative QCD. But this is ingredient, but I have to say that it's not really fully implemented in all the models as they are now. So it's a basis, but it's you should not try to get the jet cross section or something like that. It won't work. Gribov registry is very important here because it's linked the cross section that you get from data, and now we have very nice data from PP at LHC. But in fact, we would require like proton-oxygen cross section to really be more precise. And it relates to this cross-section to the particle production and multiple scattering. So it gives you some kind of predictive power, which is important in our case. And of course, some fundamental things like energy and flavor conservation. But then you have a lot of phenomenology, especially for hadronization. All the models use string fragmentation with different approach and different level of details in the different models. You could have some high density effects or in a ion collision, like in EPOS, LHC, but it's actually either completely absent in most of the model, or in case of EPOS, as we know now, it's EPOS LHC, and then it's not enough compared to what we observe now in data. We'll come back to that. You have diffraction, and actually I was disappointed when I saw the comparison with between the model and the LHC data, like what Ralph showed for Castor, that are actually these models does not do so well, and I think and it's mostly, I think, because of the hard, or I would say heavy mass diffraction, which is not well implemented in all these models. And again, having light ion data will help a lot. You have correction for higher orders, which are different in different models and which are difficult to constrain. And you also use low energy data to fix remnant, which is a forward emitted particle, the remnant of the projectile, which is very important actually for the shower development. And all these models have to have only one set of parameters, which should work for all systems at all energy, because in air showers, you won't tune energy by energy, of course. And that's really a very strong constraint on these models. And that's also one reason why we don't use a high energy physics model like PTI, Harwick, Sharpa, or whatsoever. First, because they can't collide with nuclei. So this may change with Agantir for PTI, it's nice. And also because they don't have this Gribov-Rechet theory implemented, except for Sherpa, I think, which limits a bit the predictive power where you increase the energy, but this could be improved, of course. So just to give you an idea what happened with LHC and these models, so these are CMS data at 13 TeV. So with the pre-LHC data, you have actually the data were bracketed, but you have a large uncertainties. And after retuning at 7 TeV, so these are actually prediction for 13 TeV. You see the old models at mid-rapidity do a very good job. But you already see that there is some difference when you go forward, which is important for air shower. And if you go to proton oxygen at 10 TeV, but between it's actually below this energy, you see that again, you see some 20% difference between the models. So I insist on that because I'm in the right audience, is that proton oxygen and oxygen-oxygen collision are very important for us to really reduce this kind of difference between the model. So I heard yesterday that it will be in run 3, so I'm really happy. It will be very important, especially for this kind of measurement. So this is the mean Xmax, and I'm talking about it because it's important actually as a benchmark, and when you modify the collision and the hadronic interaction, or if you introduce new physics, that's the first thing to check that you don't do something wrong. And the data are quite precise now, actually more precise than the uncertainty we get from the standard models we use. These are the 3 lines from 3 models. And this is a systematic error. So you see, actually, it's almost twice more precise in the data than in the simulation. And you have also the fluctuation of this Xmax. And that's very important because you see that they are actually a change at around 10 to 18, 10 to 18.5, also in the slope here. And this is very well explained by a change in mass composition using the standard approach. But it could be very well explained by a new physics or something like that. People try to do that. So yes, you can try. But you have to take into account that at this energy here, you can measure Xmax also with a ground signal and do some correlation. Auger did that, and you see already both components. So it's actually quite hard to explain how you could have both components in actually a relatively large amount here, and then the standard model disappear and the other one take over. But okay, maybe. But this is 10 to 18, so keep that in mind, even 18.5. Then this was shown by Oliver. It's the WISP meta-analysis. So this group of people just collected all the muon data and put it then into one plot as function of energy. And using this variable, which basically compares the data, which will be in this number, with some simulation. So these plots are always for a given model because these three numbers are for one model. And you basically renormalize, use a reference line, which is a proton simulated line, and then you divide by the difference between proton and iron to make this more robust if you have different type of observables. And then you can do one more step, which was not shown in the previous in Oliver's talk, is you can get rid of the mass dependence, this Z mass, by using the min LNA from Xmax, and you divide by the log of iron, mass of iron, 66. Which then normalize, give you a Z mass, which is compatible with this Z. And then you can plot delta Z, which is Z minus Z mass. And if the model and the data were compatible, this delta Z should just be 0 and flat. As you can see, it's not the case. These black lines are actually a fit of the data. And you see that you have a large slope, which is complete, which is like 8 sigma, not compatible with 0. And you see that the deficit, or actually the excess of data compared to simulation to 0, is as large as the difference between proton and iron at the highest energy. But what you can see on here is that this discrepancy, or this slope, actually doesn't start at 10 to 18 or 10 to 19. It starts already around 10 to 16. Actually, these data are corrected now, and it's the same behavior than here. So this seems to be more or less compatible. And then you have an increase around 10 to 16 electron volt, which is much, much lower than the change we see in Xmax. The change in Xmax is here, and the number of muons start to increase here. So to put together both things together is not so easy. So what can explain this? The main things is you can use a simple cascade model to compute the number of muons, which gives you this formula. And you have here e to the power of beta. And beta is defined like that. So it's the log of particles which are not pi0 divided by the log of the total number of particles in hadronic interactions. You can write it like this, where alpha now is just the ratio between the number of pi0 and the number on the total multiplicity. So you have basically two parameters, multiplicity and alpha, to change this slope beta, and to reproduce the data, we should increase beta by about 4%, which would mean changing, if you keep the same multiplicity, changing alpha by 30%. And this alpha depends on the hadronization. And can we change both equivalently, the multiplicity and the alpha? In fact, not, because on this plot where you have the Auger point on the number of muons, but as function of Xmax. So it's a hybrid measurement. And here you have models. So here it's QGJ24, and here it's EPOS. And then Hans Debinski here changed the multiplicity. And you see that if you change multiplicity, you change Xmax and beta at the same time. So the curve doesn't really change. It's just move up and down, but there is no real difference. While if you change only alpha without changing the multiplicity, then you get these lines. And you see that indeed, if you reduce alpha by 20 or even 30%, you could be on top of the Auger point. So you don't want to change multiplicity because Xmax is already okay. So and you won't change that. So you can only change alpha, which is related to the hadronization. So how to do that? Then you can do new physics, as was shown before. You can introduce some boson decay, or you can have a chiral symmetry restoration where you have no pi zero anymore, or strange fireball, which also reduces the pi zero. Basically, the goal is to reduce the pi zero to reduce alpha as much as possible. You can also have Lorentz invariance variation, which will change the decay of the pi zero, which not decay, etc. But there is new measurement for Auger, which is showing here, right? You have the number of muons here and the fluctuation of the number of muons here. And you see that the number of muons is indeed much larger than the prediction of the model, which are here. But the fluctuations are just exactly what predicts the models. So this means you need a model which first, because we don't see anything special at LHC, should not appear at LHC, so below 10 to 17 electron volt, but still should have fluctuations which are okay. So it cannot be like a very dramatic change. So this constrains a lot a possible solution. But at the same time, what is seen at LHC is that we see in light, I mean, in PP and with high multiplicity or proton lead on lead, we see a continuous change of the strangeness enhancement. So which could be explained as some collective effect, so maybe a coagulant plasma, but maybe just a different hadronization in light systems, which could take place in proton-air collision or pion-air collision. And if you have a coagulant plasma or something like similar, then this alpha, this ratio is actually decreased because you have much more strangeness, much more baryons, and then compared to pi zero, you get a reduced alpha. And no models really take that into account for the moment. Only EPOS has something quite close, but starting much too late because the EPOS LHC was done in 2012, before all the data were available. But we have a limitation because we know this alpha for coagulant plasma, for what we observe at LHC, and it's about 20 to 25% less than what we use in string fragmentation. So is it good enough? So a study was done to transfer this core corona approach that works well to describe the ALICE data here. So this is proton-proton, proton-lead, and lead-lead. I think you know very well this plot. So it's omega production ratio to pion. And with EPOS simulation, you can reproduce that starting from a corona hadronization, so string, to a core hadronization, coagulant plasma, but just changing the fraction of core and corona on core into even by even basis as a function of multiplicity. And you see that you can actually reproduce that very well. So what we did in one paper is to implement that in Connex on average. So as a function of energy, you change this ratio between core and corona in a smooth way like that. So starting from 100 GeV, so quite low energy, up to 10 to 19 electron volt. And you can play with how much core you have at the highest energy. So here it's 25, 50, 75, 100%. Or even some very extreme case, which would be already excluded by LHC, for instance. But in fact, these lines here, so if you go at 10 to 17 electron volt, if you look at data, you could allow maybe 75 to, I mean, about 50% of core in the particle production at LHC. It's what you need to reproduce minimum bias data, and especially if you go to proton oxygen. So this line actually are kind of compatible with what you will expect from LHC. So let's see if you implement that in the air shower simulation, you get these lines for the different scenario. So these upper lines are excluded, but these lines here are actually realistic. And you see that you get very close to data, basically within 1 sigma. So you don't really get on top of it yet. The slope is still not the same, but you are within 1 sigma, and you have to take into account that these error bars are due to energy scale, and you can move up and down all these points together. And this is due by a change of this electromagnetic to hadronic ratio that Ralph was mentioning in his talk. That will be very important to measure at LHC to see whether you have something close to what you expect from string fragmentation or something close to what you expect from a coagulant plasma, for instance. because you really have a strong influence on that. So this is more details in this paper. So what is what are the other constraints once you take all this into account? So if you look at the cross-section, this was measured by Ralph Ulrich actually, and in Auger and from the Xmax tail, and you don't see anything weird. So this is fully compatible with what you expect from LHC. So if you have something strange happening and changing the cross-section, it should be only above 10 to, this is GeV, so 10 to 5 GeV, so quite high. Then, as I said, the muon fluctuation, which are published by Auger now, depends mostly on the first interaction. So if you have a new model, it should not change the fluctuation because the fluctuations are fully compatible with what you expect from Xmax and the change in mass composition. Or you have to change both in the same way, but starting only above 10 to 18.5 electron volt, while you want to change the muons already at 10 to 16.5 electron volt, so 2 orders of magnitude below. So yeah, that would be quite difficult. And thanks to this kind of data, you can actually already exclude a strong leaf effect. Paper is in preparation in Auger. I can't show the things, but you get actually a very competitive number on leaf thanks to that. I really believe that the dramatic phase transition above 10 to 18 electron volts is really hard to get now, taking into account all these fluctuations and the fact that things start much earlier than 10 to 18. Although the photon limit gives you topological defects exclusion quite strongly, so it's a different topic, but I wanted to mention here. There's other things you can see in cosmic ray, increases fluxes like the number of muons. Right. Almost done. Where you have 20, it's a small deviation, 20 to 30%. You see in the ratio here. So these are data and these are the models. So we are lack of muons here in the increases flux. So it's low energy, very low energy. And this could actually be solved by this kind of corona approach compatible with LHC, because this will produce more strangeness and currents, and it will actually produce more muons in this region. So if you implement what we see at LHC, this probably will solve that. And also at high energy, IceCube measure TeV muons. So they see an excess of muons compared to what you expect from the models, but these models have actually no prompt component. If you increase this prompt component in a reasonable way, also taking into account the unflavored mesons decay, then you are actually good. So if you want to increase the TeV muons, you have also to be very careful, and there's not much room there. Well, where you can do more things, which is quite interesting development that was shown by Oliver's talk, is that you can use this mesons decay to get prior decay of into new particles like midi-charge or any other type of dark matter particle, which could come from photon or pi zero or J psi decay. And this actually allows, if you use this kind of detector like supercaryomecan day, if you get these particles and they are not observed for the moment, you get a flux from cosmic rays, so you can actually put some limits on the mass on the parameter of this particle. So this is something which can be done. Yeah. So to conclude again, yeah, this problem of muon in simulation is really decades old, and it was already reduced quite a lot from factor of 2 to 40%, including the baryons and pi zero, rho zero production. But there's still a difference, and I believe that this would even decrease furthermore using LHC data and the fact that hadronization and strangeness in the ends is enhanced and things like that. So this will be reduced to something quite small. At the same time, hopefully with proton PA and AA data with low A at LHC in the coming years, this will further reduce the uncertainty on Xmax prediction, and this will actually increase the constraint on the mass and the possible new model, a new physics model. And so the constraints are already strong, they will be stronger, and so it should not prevent anyone to look for something like what Oliver is trying to do. It's very nice. But I really believe that the room is getting smaller and smaller, and that even if there is something, it will be it won't be the main source of this muon anomaly. Yeah, thank you.
Thank you very much for this talk, which I think was very nicely complementary to what Oliver said. So, yeah, please, questions, David.
Thank you, Tanguy, for this nice overview. Can you comment on the high PT, so muons at large transverse distances from the air shower core? As you recall, we tried to reproduce this with heavy flavors
Yes.
and we say it appeared that we gained something, but is this solved, or does it go in the same direction as the rest of the observations of the signals, of the explanations of the signals that we observe in the data? So will all these changes that you mentioned solve also the large transverse muon excess?
So what are you referring to? Ice cube or the muon bundle?
No, Auger, you recall that we at some point there's an excess also on the. I mean, the excess in the number of muons is larger the farther you go away from the core of the shower. So the more transverse.
No, TA published something a bit like that, but Auger never claimed that. What we see is if you go to more inclined shower, the deficit in the simulation seems to increase. But not on everything is done at 1,000 meters in Auger, so you can't. There is some study internally on the LDF, on the lateral distribution, but there is nothing published in this direction. But IceCube actually can measure that, because if you go to high energy muons, you really see the tracks of individual muons, and then you can calculate the PT of these muons that Auger cannot really do. But it's different muons, and so here I don't think there is strong anomaly. And for the Auger, where you see a change with the zenith angle, which is a bit different, but this also will could be solved, I think, with this core corona thing, or with the collective hadronization, because you get more strangeness, so you get more cairns, and the cairns have produced muons with higher energy. And the attenuation length as function of zenith angle depends on the muon energy. So if you increase the muon energy, you will have more muons at larger zenith angle. But all these things that really have to be checked in details. That's a complication now we have. I mean, that's like at LHC, you have more and more data. So if you want a new model, you have to pass all the tests. And this takes time. And yeah, of course, we need, we'll wait for the new version of EPOS to check that in details. But
so EPOS right now, does it reproduce a strangeness enhancement in PA and AA?
Do we have another plot? Here. Yeah, so this is another plot from Alice, you know, I guess. So baryon to meson ratio, which is very correlated to the strangeness enhancement. And you see the data here, and this is the EPOS LHC line. And you see that EPOS has qualitatively this behavior. It goes to the value you expect from heavy ion. It starts from the string thing. But I was extremely conservative at this time, because yeah, you know, the core corona, I think, was not very popular at this time. So, so I was very, very conservative. So in fact, you see that the effect in data start much earlier than what is implemented in EPOS. So we have it in EPOS, but it doesn't have any impact, or not very strong, on air showers, because this doesn't play a role forward, and it's too rare events. But you can change actually in EPOS this, and if you can change, this is a fraction of core to corona, and corona, so this is a fraction of core in the event. And you can go from here to here, for instance, as a function of multiplicity, and this will improve that much more. And indeed, I did that for, I don't know if I have the plot here. No, but yeah, just this plot here. This is the number of muons as function of energy, and with this so-called EPOS QGP, where I just change that and actually improve the description of the statistical hadronization. The number of muons go from the blue line to the purple line, which again goes very much closer to the WISP data. but I didn't want to spend too much time on this because it's temporary. We want to have EPOS 4 with has a very good description of that, and that would be the final answer. But in fact, it really goes in this direction. If you want to reproduce that, you will increase the number of muons, and if you increase the number of muons, you will reduce room for any other scenario.
But then why do you need the proton oxygen? If with this assume, I mean, with this,
yeah, of course. Yeah, because you just, I mean, for the cross section, you need the proton oxygen. Of course, you have Glauber, but if you want to have very high precision, you need the best.
But I mean, you show here as a function of the charged particle density in the event. So you could get to the proton oxygen particle densities by going to central PP, no, in a way. I mean, if the relevant variable here is the number of particles in the final state, then you can use central PP as a proxy for proton oxygen, no?
Yes, but maybe there is other things. Like if you study proton lead compared to proton, and even to nucleus, if you look at the fluctuation, this behaves a very, very different way. And probably it's due to some nuclear effects or the asymmetry produce things. And lead is very heavy compared to oxygen. So of course, for this basic stuff, maybe it's good enough. But if you really want to look at the details and understand everything, it's better to have the data on oxygen.
And then which observables you'd like to see? Imagine that you can run tomorrow proton oxygen at 9 TeV at the LHC. What would be the first things you want to see to check things? What is the most important observable that you want to see?
For this particular, so for Xmax, we want cross-section and multiplicity and fluctuation of multiplicity. That's quite important. And for the number of muons is what Ralph said, so this electromagnetic to hadron energy ratio, which is in principle not difficult to measure. So, and as a function of multiplicity. So if you could have particle identification, of course, these kind of plots are very important. But if you can't do that, but you have access to the electromagnetic energy, like Castor could do it very forward, that's actually what we really need at the end, in a precise way. I mean, precise means 5% or something like that. So,
okay.
But more, if you can't get that exactly, the more data, the best you can constrain your model. And so. And this is a post. I mean, for Sibyl or QGZ, you have not this kind of thing. So you need the data basically to fit the model.
Thank you.
All right. Thanks for the nice discussion. It's great to have so much interest in all these things, but we're a little bit late, so I'm afraid we should move on.